So we just started looking at antiderivatives. Antiderivatives basically undoes a derivative function and gives us back our original function. And so sometimes it might be helpful, antiderivatives, if you're given some function where you're given the rate of change, something is growing, and you didn't know what the original function is, you could take the antiderivative of that to get the original function. So basically, by definition, antiderivatives are usually denoted with a capital letter. So if f of x is your original function, capital F of x would represent the antiderivative function. If you take the derivative of our antiderivative function, this is equal to our original function f of x. So notation, the antiderivative, so f of x, this is equal to the integral, which is like this elongated s f of x, little f of x, original function, dx. And so we looked at some rules here. And this was called, what we were looking right at here, this was called the indefinite integral. We didn't have
That's still f prime. Sorry, is that still f prime or is that just f of x?
That second line is just the f of x.
Okay.
So, but if I took the derivative of the second row right here, then I would get back my original function f of x. What we're working right now are with indefinite integrals. We're going to look at definite integrals later on. Indefinite integrals basically means I don't have any bounds. I'm not bounding my function in between two x values. And so indefinite integrals, we have some rules. Indefinite integrals, we always had to add a constant c. Remember, when we take a derivative of a constant, we get back 0. And so adding a constant to our indefinite integral, when we take the derivative, that goes away. Okay. If you were taking the indefinite integral of x raised to some power n, and n is a number, x is your variable, this dx is telling you what you're taking your antiderivative with respect to. And so this is telling me I'm taking it with respect to x. If you take the antiderivative of x to the n power, all you're doing is you add 1 to your exponent. So when we took the derivative, we subtracted 1. So we're doing the opposite. Instead of bringing that, what our exponent was, down in front when we took the derivative, this time when we take the antiderivative, we're dividing by our new power, n plus 1. And then we had to say this is plus some constant c. So this is saying, and I'm just going to show you real quick, and this is what we kind of talked about last week. If I have that my antiderivative of x to the n was x to the n plus 1 over n plus 1 plus c, we want to show that f prime of x, or the derivative of the antiderivative, is equal to x to the n. We can show that, then what we did and found the antiderivative is true. So if I take the derivative of this, well, that tells me that I need to bring my power down front, which is my n plus 1, times x to the n plus 1. I had to subtract 1 from my power when I take the derivative. And this was all over n plus 1 plus the derivative of a constant is 0. So notice that this simplifies. My n plus 1 in my numerator cancels with the n plus 1 in the denominator. If I simplify my exponent, this is equal to, well, n plus 1 minus 1 is just x to the n. This is, notice, is equal to my original function, f of x. Okay, so that was one of our rules, and that's what we were looking at before. And maybe we could do, some of you might not have seen the lecture. Let's actually look at a couple examples. So let's say we had we're trying to find the antiderivative of, how about 1 over x squared minus x squared minus 1/3 dx. Okay, so this is not quite in the form that I can use that general power rule of antiderivatives. I need to rewrite 1 over x squared so that that x squared is not in the denominator. And so just like when we were taking derivatives, sometimes rewriting the form was helpful. And so let's rewrite 1 over x squared as x to the negative 2 power minus x squared minus 1/3 dx. And so now we can use that general power rule. So the rule says add 1 to our exponent, and we're going to divide by our new exponent. So our new exponent in this case is negative 2 plus 1. Minus, so just like when we took derivatives and there were addition of terms, we could take the derivative of each term and then sum it. Antiderivative, same thing. So we can take the antiderivative of each term. So we're taking the antiderivative now of x squared. So the antiderivative says add 1 to your exponent and divide by your new exponent. Minus antiderivative of constant, we have to tack on x. Antiderivatives, indefinite integrals, we always have to put that plus c here. Okay. So the antiderivative of 1 over x squared minus 1/3 is equal to x to the negative 1 power all over negative 1 minus x cubed over 3 minus 1/3 x plus c. And I guess I can clean it up a little bit. That negative exponent I can bring down to the denominator. So this is the same thing as, and I can pull the negative out front, negative 1 over x minus x cubed over 3 minus 1/3. I could put that x over there, x over 3 plus c. So we can always check this by going backwards. If we took the derivative of this antiderivative, capital F of x, we should get back this little f of x, this 1 over x squared minus 1/3. It's a little f of x. So what we are taking the antiderivative of, just by terminology, is called the integrand. So little f of x is called the integrand. So the other, wanted to go over other rules that you will see. If you have e raised to some power, some constant k times x dx, when you take the antiderivative of this, this is your original e to the kx, divided by k plus c. I need to put one stipulation on that rule that we had, that general power rule up here. There's one thing that has to hold true, is that that exponent cannot equal 1. I'm sorry, not equal -1. Okay, so if n was -1, then that would look like 1 over x dx. So remember which, what could you take the derivative of and get back 1 over x? Remember the natural log of x? If you took the derivative of that, that was 1 over that x. And so the antiderivative of a 1 over x is the natural log of x plus c. So kind of thinking backwards, what can we take the derivative of to get sine, positive sine of x? So remember taking the derivative of sine and cosine, they were opposite of one another. One was positive though, and one was negative. So we know that we should know that the antiderivative is going to be cosine. We just need to think about, is it going to be positive or negative? And so, you know, it's something cosine of x plus c. And so let's just determine if it's going to be positive or negative. Well, if we took the derivative of positive cosine of x, remember the derivative of cosine of x was negative sine of x. And so that would not give me back what I had here. And so the antiderivative of sine of x would have to be minus cosine of x. So if we took the derivative of cosine of x, that's negative sine of x, times the negative out front here would give us that positive sine of x. So we could take this a little further. Remember if it was multiplied by some constant, so it was sine times like 2x or 3x, some constant k of x dx. This is going to equal negative cosine of k of x, all divided by, because we had to use the chain rule, we had to take the derivative of the inside. And so this would have to be divided by k, and then plus our constant c. So if we look at the antiderivative of cosine of x dx, it's the same kind of reasoning I did before. I know the derivative of cosine is sine, and so the antiderivative, if I took the derivative of the antiderivative, I have to get back cosine of x. And so again, I'm going to try to think to myself, is it positive or negative? So if I take the derivative of a positive sine of x, that is cosine of x. And so taking the derivative of this antiderivative gives me this back integrand. We'll be using what is called U substitution, hopefully later this week. And that's a tool to help us integrate, and it will show you this using U integration when we do that. But for right now, if you have cosine of some constant times x, then the antiderivative is going to be cosine of that constant times x all over that constant k, and then plus c. Now I'm just going to kind of jump into the other trig functions, putting that k in there. So if you have secant squared k times x, well, which trig function could we take the derivative of and get back secant squared? So remember, taking the derivative of tangent gave us back secant squared. So the antiderivative of secant squared kx is going to be tangent kx, all divided by the k plus c. Okay, so I'm just going to quickly kind of give you these because I don't have them memorized. I don't expect you to have these memorized, the next ones. And since how we're doing things online, I don't mind you having that little table right there in front of you. So the antiderivative of cosecant squared of kx dx, and this is equal to negative cotangent kx all over k. We always have to tack on that constant c until we get to definite integrals, and we're never going to put that c on there. If we have the antiderivative of secant of kx, tangent of kx dx, the antiderivative of that, so whatever thing gave us the derivative of secant tan, and that one was secant. So this is equal to positive 1 over k secant kx plus c. If it was cosecant cotangent, so antiderivative of cosecant kx cotangent kx dx, this is equal to negative 1 over k cosecant kx plus c. Kx plus c. Okay, then we also have to look at unfortunately, have to look at the inverse trig functions. So kind of going backwards. And so if you were thinking about the sine inverse of x, so that one is 1 over the square root of 1 minus k squared x squared dx. If you were looking at tangent inverse, that would be the antiderivative of 1 over 1 plus k squared x squared dx. So the antiderivative would be 1 over k tan inverse kx plus c.
Was that x cubed?
No, that's an x squared down here in the anagram. So there's two more. Sorry, I don't have a table. That would have made this so much faster. The integral of 1 over x all times the square root of k squared x squared minus 1 dx. This one is the secant inverse of kx plus c. And this says kx has to be greater than 1. And one more. The antiderivative, if you have an exponent piece, but that base is not e, so if it was a raised to the k times x dx, so the antiderivative, or the derivative when it wasn't base e, was a little harder. We had to tack on that natural log of e. And so we have to undo that. And so we're going to have a to the kx all divided by k times the natural log of a plus, plus c. Okay, let's get to the fun part where we actually get to do problems.
Now, are these all general rules?
These are all general rules, and any of the trig ones I would give to you except for cosine and sine.
Okay.
So don't worry about having to memorize the other ones, but you should know how to do the ones of x raised to some power.
Okay.
You should be able to do all of your e ones. You should recognize 1 over x too.
Okay.
But the trig ones, other than sine and cosine, I mean, secant squared, you probably should be able to recognize, but I think after a while you will.
Okay.
Okay, so for instance, like if I have the antiderivative of 1 over x minus 5 over x squared plus 1. I need parentheses around that whole integrand, and then I need to put that d and whatever variable I'm integrating with respect to. So I have to have a dx there. So right now I have a problem. I don't know how to integrate, or I think to myself, I don't know how to integrate that -5 over x squared plus 1. But by just rewriting all those problems, I noticed that that is looking like one of the trig ones. There's a rules of integration. So technically I can rewrite this as the integral of 1 over x dx minus the integral of 5 over x squared plus 1 dx. That constant, that 5, I can pull it out front. So this is really -5 times the integral of 1 over x squared plus 1 dx. So I would go look at my chart to see which trig function that looked like. And so looking at my chart, I noticed that that kind of looks like my tangent inverse. So looking back, if you look at 1 over 1 plus k squared x squared dx, this was equal to 1 over k tan inverse. Of kx. So notice, I mean, I could rewrite this if this helps you. This x squared plus 1 is the same thing as 1 plus x squared. Changing the order is not changing that. It's just my coefficient in front of my x squared is a perfect square. It's 1. And so I'm not going to rewrite this 1 over x. That was the one that had the special rule. That's to the negative 1 power if I wrote that in the numerator. If n is to the negative 1 power, that was the natural log. So whatever I take the derivative of, I need to get back 1 over x, which is the natural log of x, plus some constant, minus 5, all times the antiderivative of 1 over x squared plus 1, which I just saw was tan inverse of 1x, but I don't really have to put the 1 there, plus a constant. Well, a constant plus a constant is still a constant, so it doesn't matter how I write that constant. I'm just going to write it as plus c. And we took the antiderivative. So if I took the derivative of what we just found, I should get back this integrand, 1 over x minus 5 over x squared plus 1. So the following says, solve the initial value problem. Okay, so we're given some information about a function, and then we are trying to figure out what the original function is. And they're telling us that ds dt is equal to 1 plus cosine of t and they're telling us that s of 0 is equal to 4. So basically, this is telling me if we looked at our position function, velocity function, and acceleration function, if we were given what the velocity was, we could find what our position function was by taking the antiderivative. If we were given the acceleration, I could take the antiderivative of that to get the velocity and the antiderivative of that to get the position. So to me, I'm looking at this, that dst is kind of looking like a position function at time t, but you don't have to think of it that way. But that ds dt is telling me that's the derivative of s. So we want to figure out what our original function is. So another way to say this is saying s prime of t is equal to 1 plus cosine of t. And we want to find s of t. Okay, so I know that S of t is going to equal the antiderivative of S prime of t, dt. So S of t is going to equal the antiderivative of that 1 plus cosine of t dt. Okay, so the antiderivative of a constant is that constant times the variable you're taking the antiderivative with respect to. So the antiderivative of 1 is 1t, right? If I took the derivative of t, that would get me back my 1 up here. And now I need to take the antiderivative of cosine. So antiderivative of cosine, that would have to be negative sign. So minus sign, is that right? No, it would be plus sign. Let me just think about it. So if I took the derivative of sine, that is positive cosine. So it is sine of t. Plus, I have to add in some constant c. We're given, though, enough information, because this is an initial value problem, we're given information that we can figure out what c is. We were given that S of 0 was 4. Well, that's telling me my S of t value, my y value, if you want to think of it as y, is 4, when my variable t is 0. And so I can solve for c. So I get 4 is equal to t, which is 0 times, 0 plus, sorry, sine of t, which is 0 plus c. Well, sine of 0 is 0, plus the 0 out there is 0, plus c. So I get 4 is equal to c. So my function, or S of t function, with that information is going to be t plus sine of t, plus what I just found my constant to be, which was 4. So if I took the derivative of that, I should be able to show that that is 1 plus cosine of t. Okay. What if you were given d cubed y all over dx cubed equals 6? You were given that y double prime of 0 equals negative 8. You're given y prime of 0 is equal to 0. And you're given y of 0 is 5. And we want to solve that initial value problem. So we want to find what y is. So basically that d cubed y, that's basically saying the third derivative of y is equal to 6. So I know then that the second derivative would equal the antiderivative of the third derivative. And this is in terms of x. So if I took the antiderivative of 6, that would give me 6x plus some constant c. And I'm given information about the second derivative. I've given that the second derivative when x is 0 is -8. So we can use that to figure out what c is. So we know -8 is equal to 6 times x, which is 0, plus c. So in this case, then that c has to equal -8. So really our double derivative of y is 6x minus 8. So I'm wanting to get to my original function. So if I have my double derivative, I could figure out what my first derivative is by taking the antiderivative of the second. So y prime of x, this is equal to the antiderivative of 6x minus 8 dx. So I can use my power rule. Power rule says you're going to add 1 to your exponent. So adding 1, I get plus 1 to my 1. Divide by your new power. So divide by 2 in here. Minus a constant. So that constant times x. So minus 8x plus c. So we have the first derivative of y is equal to, I notice my 2 goes into my 6, so I can cancel. And that would just leave me with 3x squared for the first term, minus 8x plus c. But we're given information about the first derivative, so we can figure out what c is. We were given that, oops, wrong thing. We were given that y prime of 0 is 0. So plugging that in, okay, we get 0 is equal to 3 times 0 squared minus 8 times 0 plus c. That shows me c is equal to 0. And so my first derivative of y is equal to, where is it at? 3x squared minus 8x. So we're almost there. We could figure out what y is by taking the antiderivative of the first derivative. So take the antiderivative of 3x squared minus 8x dx. So I have 3, add 1 to my exponent, so 2 plus 1, divide by my new exponent, well, 2 plus 1 is 3, minus 8, add 1 to my exponent, so 1 plus 1, divide by my new exponent, which is 2, plus my constant c. So y of x is equal to, I know there's my 3's cancel. Oh, I won't do that. Oh well. My 3's cancel and I'm left with x cubed minus, should be x. 2 goes into that 8, so that's going to give me minus 4x squared plus c. Sorry, I'm going to go up and grab so we can figure out what c is. Maybe. Oh, wow. What was it? Y sub 0 was equal to 5. Okay, so when y is 5, x is 0. So we have 5 is equal to 0 cubed minus 4 times 0 squared plus c. So c has to be 5. And so knowing that, we now have our original function y of x. So y of x is equal to x cubed minus 4x squared plus 5. What happened there? Oh. Okay, so that is pretty much antiderivatives we're going to look at, and that's the end of chapter 4. So we're jumping into chapter 5, which is all on integration, techniques of integration, looking at the different ways that we can interpret integration. So let me just kind of give you a preview for tomorrow. So maybe you were given something that looked like this. And this was y is equal to um, 9 minus x squared. We wanted to find the area. Under the curve. Well, you could probably do that because I noticed that that's just a quarter of a circle with a radius of 3, but you might not have noticed that. And we could probably do some reasoning like that. But the whole point of this next section is that we're going to create rectangles inside of where we're trying to find that area. And so notice if I created one rectangle, right? We could get an estimate of what that area is. I could say, okay, well, I know in that case, that's a square, 3 times 3. So approximately 9 square, whatever I'm looking at in terms of units. But notice if I then break it down into 2 instead, 2 different rectangles. So maybe I did here to here, and then I did here to here. This would even give me a better estimate. But instead, if I decide to go and do it in terms of maybe 4 rectangles instead. So maybe like this, this, and this, whatever. The more rectangles I do, I know how to find areas of rectangles pretty easy, right? Length times width. And so if we can find the area of each rectangle and sum those areas, then we're going to get a close approximation of what's under that curve. Well, the more rectangles that we create, the better and more accurate that we're going to get to that exact area. So kind of similar to what we were doing with limit, the closer and closer we got. In this case, the more and more triangle or rectangles we get, the better approximation of area that we're going to get. And so that's what we're going to be looking at for the rest of the week, pretty much. Pause.